Good evening, everyone. I am Wes and Joint Seminar Manager of QISCA. It is my pleasure to introduce today's speaker, Wonseok Huh from EQS. Wonseok Huh is currently senior for the Department of Physics in KAIST and the lab member of Quantum Optics and Quantum Information Lab led by Professor Young-Sik Lam. Today, he will be presenting a talk titled Time-Bin Entanglement and Bell-Type Inequality Violation, sharing insights from the paper High Visibility Time-Bin Entanglement for Testing Chained Bell Inequalities. Tomasin et al. Please join me in welcoming Wonseok Huh to the stage.
Can everyone hear me?
Yes.
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 Okay. So my name is Wonseok Huh, senior undergraduate at KAIST, and the title of the paper that I'm presenting today is High Visibility Time-Bin Entanglement for Testing Chained Bell Inequalities. To understand this paper, we need a few prerequisites. First is the basic notion of quantum entanglement. Quantum entanglement is often used in quantum technology such as quantum communication, metrology, and computing. So quantum entanglement is very important to implement such quantum technologies. And there are various ways to implement this quantum entanglement. For example, in the qubit state, which is composed of two orthogonal states 0 and 1, we could use linear optics and use the polarization of photons to implement them. For example, in a qubit system, we could use the horizontally polarized photon as H, a 0 state, and the vertical polarization photon as 1 state. And using this, we could make quantum entanglement as shown in the below diagram. I'll skip the mathematical parts and explain them using the diagram. For example, suppose we have the red and blue photons in an entangled pair of HH plus VV state. Then if the red photon is measured to be horizontally polarized, then the blue one is automatically decided as H. And the same holds for vertical polarization. However, they cannot be in either HV or VH state, and this is basically called the quantum entanglement. Another way to implement this entanglement is the energy-time entanglement. Unlike the previous slide, which uses the polarization regime, the energy-time entanglement is usually continuously changeable. For example, suppose we have a three-level atomic system like the diagram here, and after the state is excited into the upper state of psi 1, it has a long lifetime of T1. And it decays into the second level, which has a shorter lifetime of T2, then the red and the blue photons will be correlated in time uncertainty very closely. For example, we don't know when either the red or blue photons are going to arrive at the destination. However, if one of the photons arrive, then the other one is automatically determined within the time uncertainty of the short T2. So they are correlated in energy, in time, and the Heisenberg uncertainty principle also limits their uncertainty in the energy regime. So this is called energy-time entanglement. Another prerequisite that is required to understand this is the coherence length. This is basically a measure of how long a pulse in light maintains its sinusoidal shape. And this is given as speed of light times the coherence time. The Fourier transform is often used to analyze this in the spectrum regime or the spatial regime. And the more broad in spectrum, the shorter the coherence length, and the more monochromatic the light is, it has longer coherence lengths. And the most important part in this slide is that for first order interference to occur between two lights, we need them to have length difference within the coherence lengths. For example, typical helium-neon laser light that uses extra cavity has coherence lengths of about centimeter to meter order. So if we implement the Michelson interferometer, then we need the two arms to have length difference at most at meter for the interference to occur. So why did I talk about the coherence length? Is to talk about spontaneous parametric down conversion. This is an optical system that can easily create energy-time entanglement that I just talked about. So in this process, the pump laser, or the blue light in the diagram, is pumped into the nonlinear crystal, which probabilistically creates two photons, signal and idler, which has 810 nanometer for the 405 nanometer input wavelengths. So they must satisfy the energy and momentum conservation, and this sets some limits on the coherence length of the photons. For example, the initial pump light, the blue one, has energy uncertainty that is related to its coherence time. And the produced photons might have uncertainty on each on their own. However, the sum of their uncertainties is limited by the initial pump laser. So this is some notable thing that we should remember about this SPDC process. Next is Franzen interferometer, and this I introduced to understand what time beam entanglement is. Time beam entanglement is the main focus of this paper, and that is really strictly related to energy time entanglement, so I'm going to explain first what this is. The 1989 paper made by J.D. Franzen suggested this kind of interferometer, and the atom in the center produces two photons at like this three-level state. So the red and blue photons are correlated in time very closely, and they are each sent to right and left arms, which is composed of the short and long paths L1, S1, S2, and L2. So in this case, the paper mathematically analyzes how interference between the short paths and the long paths can occur. This is quite surprising because the produced photons each have a very short coherence length, and the length difference between S1 and L1, for example, in this case, is at the order of centimeter, but the coherence length of each photon is at the order of micrometer. So the interference should not occur if that is the case. However, the coherence between the short and the long paths, the coincidence counts can occur by mathematically analyzing in this way. I'll skip the details. And this is mainly because the sum of the uncertainty of each photon is limited by the initial pump laser. So as long as the initial state has long enough coherence length, then interference can still occur. So using this, we could create a time beam entanglement, which is discrete version of energy time entanglement. I previously talked about how energy time entanglement is continuously changeable because, for example, time is not discrete, so it could be produced at any time within the uncertainty. However, by using this Franzen type interferometer, we could make them either into short paths or the long paths. So we only have two time beams, and this is the discrete version called time beam entanglement. And they can quantum mechanically interfere because of this mathematical result. So far I talked about what time beam entanglement is briefly. And next is the EPR paradox. Why do I introduce this? Is because the paper focuses on violating the Bell-type inequality using time beam entanglement. And to understand what that inequality is, we need to know this. EPR state is basically a paradox suggested by the three scientists, Einstein, Podolsky, and Rosen, I think. And it basically says that the quantum entanglement and its interpretation in quantum mechanics violates the special relativity. It's also called spooky action at a distance. However, to explain this, they suggested a local realism interpretation, which means that there is some locally hidden variable lambda, which we do not know about. So the quantum entanglement is not actually determined at measurement, but they are predetermined. But the problem is that we just don't know what that lambda is. So it is called a local realism. And this can be categorized into a few categories. I borrowed this slide from Professor Youngshik Ra's Quantum Information 1 again. Anyways, in the quantum system, we basically have non-quantum, classical state, which is the separable state in the inner circle. And then the local hidden state model mathematically can explain entanglement. And beyond that, we have the local hidden variable model, which can mathematically explain steerability. And finally, if we violate the local hidden variable model, then we have non-locality, which is the final destination we want to get, because this proves that local realism interpretation is false and quantum mechanics is indeed right. And to prove this, we use some, before that, this is the mathematical model for local hidden variable theory. And to prove that quantum mechanics is right and local hidden variable theory is wrong, we need to violate some kind of inequalities. For example, the HSH inequality, and this is suggested by the four scientists as shown in the title. We use this kind of inequality because this is sometimes easier to implement in the experiment compared to Bell inequality that is already famous. And so basically, for example, CHSH inequality is like this. Suppose we have polarization state photon as the input state. So we could choose which basis to measure. It's either 0 or 1. For example, Alice can measure the photon state in the 0 basis as horizontal and vertical polarization, whereas if Alice chooses the 1 basis, she is measuring at 45 degrees or minus 45 degrees basis polarization. And each result has either +1 or -1 depending on the measurement. And Bob also selects two kind of bases, y equals 0 or y equals 1. And they finally calculate the expectation values as shown below. And if this value is lower than 2, then it can be modeled by local hidden variable theory. However, if it is violated, then we could suggest a quantum correlation. Yes, this is the inequality that I just talked about at the top. However, in polarization regime, it is easy to violate such inequality, but in time-beam entanglement case, there are some loopholes. For example, besides the SS and long states, we also have the long-short and short-long combinations. And skipping the details, this limits the visibility of interference to 50%, resulting in the local realism model to be able to achieve the inequality value as high as 3. But quantum mechanics usually give the result of 2 times square root of 2, which is smaller, which is in between 2 and 3. So we cannot preferably violate the Bell inequality. So in this paper, they used the chained Bell's inequality instead. Previously, we saw that Alice and Bob selects either 0 or 1. So we have 2 types of bases. But we expand these 2 types of bases into n type. So basically, we measure either in 0 basis or 1 basis or 2 basis up to n basis. And this kind of inequality is changed into the inequality below. This is chained Bell type inequality. So in this paper, we utilize this to violate such inequalities. For example, quantum mechanically, they calculate that for the n case, the expectation value of the S shown here is calculated to be 2n times cosine terms, and local hidden variable model calculates them as 2n minus 1. And the quantum mechanical value is higher, which means that we violate the inequality only when 2n is larger than 6. There's a typo in the inequality. So we need n to be larger than 3. And this is the ideal case where the experimental visibility is 100%. So if the visibility is lower than this, then the inequality is weakened. So practically, they say that we need at least 94.63% visibility to perform this violation. This is the basic experimental setup they use. First, we have the second harmonic generation to produce blue light. And after going through some stabilization formation, they are inserted into nonlinear crystal denoted by SPDC, which was spontaneous parametric down conversion. And finally, the 2 photons go into each arm, DA and DB, which stands for Alice and Bob. Each Alice and Bob has the short and long pass performed by the Michelson type interferometer as shown in the diagram. So they finally detect the 2 photons at DA and DB. This is the experimental results. In figure 3 on the left, we first have the manifestation of time-beam entanglement. Why are there 3 peaks in each graph? This is because we have 4 combinations, SS, LL, SL, and LS. And this graph shows the time difference between the arrival time of 2 photons. Photons were in the SS state. It means that they both go into the short pass. Then they will arrive exactly at the same time, meaning that they will be recorded in the center peak, which means 0 time difference. However, if one photon was in short path and the other was in long path, they have a few nanoseconds time difference, and it will result in either the left or the right peak depending on SL or LS. So SS and LL are superposed in the center peak, and the SL, LS states are each presented in the side peaks. So if we post-select the center peak, we have the SS plus LL superposition, meaning that there is quantum entanglement between these two time beams. So this is the experimental manifestation of time beam entanglement. On the right, we have the visibility of this interference pattern by using the piezoelectric voltage. For example, in this state, the long path of the Michelson interferometer is slightly adjusted by using piezoelectric voltage. So, yeah? Yes, yes.
In this case, we can distinguish SS or LF. We cannot distinguish.
Yeah, that is the point. We cannot distinguish between SS and LL just by measuring the coincidence time. So that is where the quantum entanglement occurs.
The difference is shorter than Fourier's time.
Yeah. Right. The time window should be short enough to.
SS is faster than LF, but the difference is very, very low.
So this experimental result measures the time difference of the two photons, but we cannot know the absolute time that they arrived in. For example, if they arrived at time t equals 0, okay, let me explain this again. This type of measurement is called TCSPC, time correlated single photon detection. And if one photon is detected in dA, then the other photon detected in dB is recorded with respect to the time when dA arrived. So it only shows the time difference of the two photons, but we cannot know when it arrived in absolute time. So that is why we cannot distinguish SS and LL, because they only measure the difference between the two photons. Yeah. So practically, we do need to adjust the experimental setup really closely so that they are exactly matching within micrometer units. So it is hard to implement Friend's time beam entanglement. Anyways,
I also have a question.
yeah, sure.
Is this a single photon experiment?
We have the two photon prepared from the SPDC process. So I think it's exact to say two photon experiment. A photon pair experiment.
No, but before going through the SPDC, it has to be a single photon, right?
Yeah, that is correct. But practically, we use continuous wave laser. So probabilistically, single photon is converted into two photons. But yeah, but the input state itself is not single photon. It's just probabilistically selected inherently by SPDC process. Anyways, you're right about that point. Any more questions? Coincidence window size is determined by the experimental equipment device. For example, the one that I'm using in my lab right now has best resolution at 0.25 nanoseconds, so 250 picosecond time window. And time window must be small enough to distinguish the side peaks, because for example, if time window is 6 nanosecond in this case, then the three peaks will all be shown as one big peak. However, this is possible because the time resolution is very short. So in order to post-select the SS and LL peaks only, we need to have short enough time window. Yes, but that is technically limited at some point. If there are no more questions, then I think I should proceed. We are almost at the end. On the right, we have the visibility of the Franzen interferometer, and they acquired about 99.4% at most, which is higher than the 94.67% that they suggested should be higher than to violate the Bell inequality. And finally, they measure the S value, expectation value for 2n equals 6, 8, and 10 cases because we saw that n should be larger than 3 to violate the inequality. And for that 3 cases, they obtained the value of 5, 7, and 9 with some variances. And yeah, so they successfully suggest that they violate the Bell's inequality. This is the conclusion. First, timing entanglement. Okay, I think I forgot to talk about this. Why are we so keen to make this time being entanglement into high visibility and make quantum entanglement, which is harder than polarization? That is because time being entanglement has higher inherent noise rejection compared to polarization encoding. So if we are able to make good enough time being entanglement, that it could have some advantages over the polarization ones, although it is harder to make right now. And in this research, high visibility of more than 99% was achieved, and this was used to prove violation of Bell-type inequality. So in conclusion, this experiment will open the door for time-based QKD, quantum key distribution applications, as the author suggests in the paper. Thank you for listening.
Okay, I have a simple question.
Okay.
What exactly is the visibility?
Visibility in optics is maximum value minus minimum value over maximum value plus the minimum value. So if the minimum value is almost set to be 0, then we have 100% visibility, which is ideally the most exact case in optics experiment. It is, yeah, that is visibility.
Okay, and I have another question. Regarding applications in QKD, obviously you have to use certain distributions for like quantum communication. You have to use a single photon, but I believe this experiment is not for a single photon experiment, so I'm not like fully convinced how it could be like.
Can you repeat the question? Is howling a lot?
So it's howling.
왜 울리죠? 그래요? 네. Yeah, can you repeat slowly?
Okay, it's still howl?
Yeah, they're still howling.
Okay, then maybe I'll just ask via chat.
Okay, okay. chat. 이거 아니고. 보이시나요? 저기 있다. 감사합니다. 근데 뭐 다른 매수죠. 그러게요. You could also use the chat to ask other questions. I'll wait a few seconds. 예. 방법으로 그 인테그러먼트를 구현하는 게 더 개선되는 게 있나요? 어떤 점이 개선되나요? 최근 논문 중에 타임비 인텐그먼트를 찾아본 기억이 없기는 한데 그건 더 찾아봐야 될 것 같습니다. 네. 네네. 완전 인텐그먼트의 단점이 뭔가 아니면 더 타임비 인텐그먼트 연구는 사실 많이 진행되고 있어서 최근 논문도 많은데 제가 읽어보지 않은 것뿐이고요. 그 장점과 단점을 장점은 얘기했으니까 단점을 얘기하자면은 타이밍 인텐그먼트가 아무래도 거리 차이를 이용하는 인텐그먼트가 있다 보니까 페이스 시프트에 엄청 민감합니다. 예를 들어서 하나의 패스 쪽에서 거울이 뭐 온도 0.1도 변하는 거에도 민감하게 떨릴 수가 있고 우리가 기침 한번 하는 거에도 떨릴 수가 있기 때문에 그런 것들을 보정을 해줄 만한 기술들이 필요한데 대표적인 게 페이스 러킹이라고 있습니다. 다른 레이저를 따로 그 거울에다가 씌워주고 이제 그 비지빌리티가 한 로케이션에 고정되도록 거울을 계속 수시로 바꿔주는 거거든요. 코딩을 통해 가지고. 그래서 그런 페이스 락킹을 사용하면은 타이밍 인텐글먼트를 안정화시킬 수 있지만은 그게 약간 번거롭다는 단점은 있습니다. 네. 예. 네, 그 정도 단위 또는 그 이하로 안정화를 시켜야 되기 때문에 쉽지는 않습니다. 네.
그래서 어떤 뭐 문제 때문에 체화식의 부등식에서 2가 클래시컬인데 뭐 수분 뭐 여기서 3
예.
3을 넘겨야 돼서 n이 3 이상이어야 됐던 걸로 기억을
아,
하는데
네네.
n이 3 이상이랑 메저먼트가 3개 이상인 걸 앨리스 밥, 찰스도 있듯이 뭐 이런 식으로 돼 있는.
아, 그 부분이 클리어하지 않았는데 앨리스 밥 찰스까지 있어야 된다는 게 아니고 앨리스 밥이 아까 각각 측정을 할 때 0 또는 1 베이시스라고 받는다고 했는데 그게 아니고 0, 1, 2, 3, 4, n 베이시스까지 필요하다는 뜻입니다. 예. 네. 아, 그거 제가 말씀 안 드렸는데 원래는 폴라리제이션에서 그냥 매저한다고 했잖아요. 근데 그거를 n3 이상 넘어가면 쉽진 않으니까 여기서는 페이즈를 이용했습니다. 그러니까 피에조 일렉트릭을 이제 6분의 파이 뭐 볼티지를 주고 6분의 3 파이를 주고 6분의 5 파이를 주면 각각 거리가 조금씩 미세하게 달라지는데 그 각각에 대해서 이제 플러스 1, 마이너스 1을 측정하는 거죠. 네네. 모드 모드라기보다 그냥 페이즈 차이를 그냥 단순히 측정한 거죠. 예, 페이즈만. 아까 질문 주신다는 분이 질문이 없으셔서 예. 한 10초 기다려보고 질문 없으면 끝내도록 하겠습니다.
I have a question actually.
아, 오케이.
I don't know if I'm asking the right question, but what's the difference between a continuous laser source and a bunch of single photon sources?
Uh, it's you can easily think about it as very low intensity laser as the single photon sources and just normal intensity laser as continuous wave lasers. For example, if we in the photonics interpretation, certain intensity of a light can be calculated as each photon's energy times the number of the photons. But if you make the intensity lower, lower, and lower until it is almost at the order of single photon's energy, then we only have few photons at that case. So very low intensity laser can be thought as single photon sources.
But I understood this experiment as using a single photon and splitting into two entangled photons, right?
Yes.
But you said that we use a continuous laser source as the
Ah, right.
experiment.
So
yeah.
when is the continuous wave laser converted into single photon source? That is in the SPDC process because spontaneous parametric down curve conversion inherently has very low probability to occur. For example, 1 in 10 to the 4 or 6th order of the photons can make the photon pair. So this very low conversion rate allows us to create single photon sources from the continuous wave laser.
Thank you. Okay.
You're welcome. Then I'll also count down from 10, I guess. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Thank you.